All right, don't do anything embarrassing. It's being recorded now. Okay, so what we're going to talk about today is these two crazy cross product formulas down below. And I think I can explain them in a way that you go, well, that's kind of cool. That actually makes sense. Have you even ran across in a math class cross products yet? What class was it in? Vector calc?
Linear algebra.
Yeah, linear algebra and vector calc. They're kind of a hard idea to get your mind around. But it's a cross product that you take. It's a product does multiply, but then you cross because you're multiplying diagonally, and then it's done with vectors. So cross product is kind of a way to multiply two vectors together. But the problem comes when you try to make sense of it, because until right now today, I bet you don't understand it. Like maybe you can do it, but I bet you don't understand it. But you will actually after today, I hope. And then later there's something called a dot product, which is another way to multiply two vectors. And so it's like, what? Like how can it's like saying 5 times 6? There's 2 ways to do this. No, there's not. There's like the answer is 30. But there's 2 kinds of products. But the problem is when you try to understand them, you have to understand them in an engineering context or they make no sense. Like it's engineers that invented this stuff. So we're going to learn what a cross product is today in context of a couple problems. And I want to bring up something we did the other day. Memorable moments. I just want to remind you of something that I said the other day. Do you remember how I kind of pointed it out that we ended up, and I even took the time to write it out. We took the force, which was in the X direction. Grab a pen. We realized we had to break down her forces because her force was coming in at a weird angle. And since we said the force had to be perpendicular, we said it would be way more trouble to leave 170 alone and to try to come up with this perpendicular distance here. So the force is going this way and the distance has to be perpendicular. And since we were rotating around that point, we said it'd be way more trouble to find that distance than to leave these sort of rectangular distances that we have alone. Well, why don't we convert the 170 into horizontal and vertical components? But the weird thing is then there's 2 of them. There's not one force, there's 2. And so what we noticed was the X force, which would be horizontal, since torque or moment is force times perpendicular distance. Notice that distance could be moved to be over here, so it's right above that point. But we noticed that force X actually got multiplied by distance Y. Does that make sense? And then we took force Y, which is going this direction, and it got multiplied by distance X. And so if I was to try to make kind of a mnemonic device for this stuff right here, so this is kind of the logic for a cross product. And we didn't need a cross product here because we're actually able to draw pictures and see it. So that was kind of like the scalar technique. I'm seeing the numbers and I'm able to visualize this. And I like that stuff. I like it. So okay, I can touch this. It makes sense to me. But the logic of a cross product is kind of where you say, okay, well, this will be our force row, and this will be our distance row. And then what I'll do is I'll put my forces in here. Our force of X was 97.5. And our force of Y was 139.3. And our distances were 4 and 3. Let's see, our Y distance was 4. So I put my Y distance here. And my X distance was 3. So does it make sense? Like, that's where force goes, and sort of this is like ordered pairs. This is our X's and this is our Y's. Does that make sense? Now, here's where the cross product part comes in. Maybe you can already see this. Like, what do I do to that little matrix there? So I'm drawing out my matrix. It's got rows and columns. Rows are force, rows are distance, and then columns are X's and columns are Y's. Let's see, if I write it that way, I could actually mechanically get the answer to this question if I multiplied these diagonally. Now, let me say one more thing that's kind of tricky about this. So that's kind of neat because maybe you can see I could multiply these diagonally, but some of you that have taken this before, when you multiply those diagonally, doesn't that achieve the same thing we just did up above? But what do you do with those two answers when you multiply them diagonally? What do you do with the two numbers? You're supposed to subtract them. And again, if you've never seen that before, which you shouldn't have, frankly, it's like, what are we subtracting? Well, the problem is you got to be really careful with this drawing. In other words, let's see here. This force X right here, its distance is in that direction. I think I'm doing this right. It's in that direction, so it actually means it's down 4. I think I have that right. But I can't remember off the top of my head. Am I measuring from the force? I think I'm actually doing this backwards. So you got to be careful with signs. And so this cross product idea is let's let it take care of itself mechanically. Like let's not understand it. Let's just stick the numbers in a matrix and have this process take place, and then we just get the right answer, even though we have no idea what we're talking about. So that's why I said I kind of prefer the method we did in class a little bit better. But you can appreciate if we're going to move to 3D, it's going to be very hard to draw pictures like this, right? And so that's why we kind of need to know this. So let me see if I can get this right. So if I measure from and I'm sort of glad I have to kind of sit here and think about this a little bit. I'm looking at your note sheet right now just because I want to see if I can do something that will help you. Yeah, okay, I think I got it now. So if I'm going to be careful with signs here, then I got to think, okay, everything is happening around point O, around this point, that's what it's rotating around. So from that point, does it make sense force X then would actually be negative because it's going left? And then from this point, this is actually up 4, so that's a positive 4. Does that make sense? Am I doing that right?
So what you're doing is not doing Cartesian. So you know how counterclockwise would be positive and clockwise is negative? Basically eliminating.
Well, the torque is positive and negative.
You're assigning the negative and positive for the matrix. Because you said it's to the left. But if it was to the left, it would have been positive as a Cartesian.
Yeah, you may be right. That's kind of bugging me too.
If you do it just as a regular graph without it being Cartesian, it would be negative because it's on the left side.
Yeah, I may be screwing up the signs here, but that's good because it sort of helps us. Because in a sense, I always do the 2-dimensional ones based on logic. When we move to 3 dimensions, this will take care of itself a little bit better for you. But I think this is actually still right. And then look at force Y. Well, from here, notice force Y. Force Y is left 3, which would actually also be -3. That'd be -3 because it's actually left 3. And then force Y is aiming down, so that means that would be negative. So I think I have the signs right there.
Yeah, because it ends up to be a negative answer, but the force is being applied on the left side. Because you'll get a left number and then you subtract, and 2 left will be turned positive, but you still have the minus. So then it's a negative minus a positive number.
Yeah.
-3 turns a negative 139. So it turns into a positive, but you still have minus sign from subtracting.
But the positive on the left minus the negative.
On the left, you'll still have a negative because it's a negative 97.5 times 4. So you have negative 9 times 4 minus the -3 times -39.
Oh, actually, I know what's wrong with this. I have the signs correct. So we are measuring from here. And so I have this correct, but what I have backwards is the distance has got to be on top and the force is going to be on the bottom. Now, do you see the problem with anything that represents memorization in the sense that, because notice I'm sitting here struggling with it. If you memorize something, you got to be really careful to kind of like put everything in just so. And so the cross product is just saying, hey, if I wrote in the forces and the distances like this, and I multiply diagonally, wouldn't that accomplish what we did the other day up here in blue? I mean, that would accomplish that. However, up here, didn't it come out positive 807? And so if you multiply diagonally here, you would get a negative times a positive when you multiplied this way, and you'd get a negative number. And then it turns out that when you put it in this form, like this isn't going to work unless what you do is you don't multiply diagonally and add. So this little cool mnemonic trick is you multiply diagonally and you subtract. So I'd have a negative number, the way I wrote this, I'd have a negative number, and then you always subtract, and then I'd have a negative times a negative, which is actually a positive number. So I'd have a negative minus, and so I would get 807.9 for this, except for I'd get a negative. Now that's wrong because the answer is positive. In other words, it is spinning around the axis positively. And so this is how this was invented, is somebody saying, how am I going to do this so that I can do it in 3D and still survive this? Because I'm not going to be able to draw pictures. Let me see if this fixes it, because on your note sheet, it actually shows this is reversed. In other words, the distance goes on top and the force goes on the bottom. And so -3, +4, -97.5, and -139.3. Does that fix it? Can you see somebody inventing this, if you will, like trying to figure out a way to just do this automatically? And so the way a cross product works is you take this number times this number. So you start that way. And so the downside of this is you actually got to keep this straight. It's not that you just multiply diagonally. You got to know which one goes in front because you're subtracting. So I always start with that one. So negative times a negative, that's going to be a positive. 3 times 139.3. I got 417 for that. And then secondly, you multiply this way. It doesn't really matter which direction. And so then this is always a minus sign, always minus. And then 4 times -97, 4 times -97.5. Well, that's actually a negative number. So we get -390. And so because you're subtracting a negative, you get a positive, and then we get that same 807 answer. So do you see how there's actually a genuine choice here? There are some people that say, I'd rather draw all the pictures and like make sense of it, touch it, which again is my temperament. And other people are like, no, let's automate this, man. Let's just automate the process. Does it make sense? It wouldn't be hard to teach a computer to take a cross product for you and just like, bam, pops out 807. There's a good argument for that. My tendency when I'm first learning something is to want to touch it as much as I can, but I can see if I was doing this every day as an engineer, there was some software I could set up where I could just kind of plug the distances and forces in and have it spit it out. I could see that I would probably be able to switch to that later on, but they both have merits. It's kind of my point. And so what I want to show you now is this. So you should be happy with this. Moment of a force about a point is force times distance, and it's important to understand that the distance has to be perpendicular. But now we're going to move to 3D. And so we got to look at 5 and 6. And so how do you find the moment of a force around a point in 3D? Well, does it make sense instead of just having a distance in X and a distance in Y? So that R is kind of like R for radius. That's distance. That's what we just did. Except for now, we're also going to have a distance in Z. And notice what that says here. Rx, Ry, and Rz are the Cartesian lengths from O to the vector. Isn't that what I just did a second ago? I went from the point up to the force, not from the force down to the point, but from the point up to the force. And so that's a very carefully made this note sheet myself. Like you got to actually look at every single thing it says. So that's those 3 distances. And then, as we just did a second ago, aren't these F's forces? But again, what do we have? We have a force in X, a force in Y, and a force in Z. So a second ago, our matrix was just really this right there, wasn't it? And so do you see how it just got a hair bigger? That's it. It's got a hair bigger. However, you can probably appreciate, like, how am I supposed to multiply diagonally now? Because it's like, there's not just 4 numbers anymore. So it's like, what do I do? Can you appreciate somebody probably spent a lot of time trying to figure out, wait, now what gets multiplied by what? And this gets subtracted. And so this process ends up rather weird. Now, let me just give you the gist of it. Let's see, let's just go back to, let's go to a blank note page. So on the top of that note sheet, there was just our placeholders. In other words, we agreed that I, J, and K would help us keep straight which one's X, which one's Y, which one's Z. And then there were just numbers down here. So I'm just gonna write a bunch of numbers that make no sense at all. Every one of them different. So how do you take a cross product of this expression right here? What is the cross product? Well, here's what you do. You start out with this and you sort of cross out that row. This is crossing this out is going to kind of give us our I row. So that'll be I. And do you see what's left behind? What's left behind is this little, well, 2 by 2 matrix. And we know how to take the cross product of that. We go 5 times 3, always minus 4 times 2. Does that make sense? And so there's our I value, sort of our X value of our rotation. Okay, cool. Then what do? Then we move to the next one where we cross out this row and this column. What matrix is left behind there? Well, notice it's a little kind of harder to see, but it's basically these numbers. Does that make sense? So I go 7 times 3. So this is our J row. 7 times 3, which is 21, always minus 8 times 2, which is 16. And so it actually isn't new. You just have to do it kind of a chunk at a time. Lastly, what do? Maybe you can see where I'm going with this. Lastly, we say we cross out this row and this column. And so that leaves the 7, 5, 8, 4. So 7 times 4 is 28, minus 8 times 5 is 40. And that's kind of our Z or our K row. So let's see, what is this? 15 minus 8 is 7. 21 minus 16 is 5. And 28 minus 40 is negative 12. And so that, and then there's one other weird thing. Any of you have taken this? What's the weird thing here? The moment then of the vector version of the moment. And that's what's kind of hard about this is you don't get a number for this. You actually get a direction ultimately. You get an arrow pointing someplace for this. That's what you're getting here. And so you say that as but oddly, the signs actually swap. Again, this is some nerd just trying to figure out how to automate the process. Unfortunately, even that isn't simple enough. This first one is actually the sign that it is. The second one, you actually have to change the sign. And the third one, you leave alone. So it turns out the first one is 7i. The second one was positive 5j, but it's actually negative. And the last one was negative 12k, and you just leave it alone. And so that's actually the vector answer. Now, here's the concept of kind of how this works. In the end, what you're getting, does it make sense if I say, hey, let's rotate this podium right here? Does it make sense to have a lot of options as to how to do that? Does it make sense I'm rotating it around this axis right now when I spin it like that? But is that the only way it'll rotate? Can't I rotate it that way too? So when you talk about how much torque there is in 3D, you can't just say how hard it wants to rotate, because you got to also describe which way are we talking about it rotating. So when I'm spinning it this way, rotating it around this axis right here, that vector is basically sticking straight up. In other words, it's along that line. And so that's telling me that vector, the direction it's pointing, it's basically saying this vector right here, yeah, it's actually rotating around that. That's what it's rotating around. So it's giving you the arrow. And then if you did Pythagorean theorem with these three numbers, then you would actually know how hard, how many Newton meters of desire to rotate that has. So you're kind of getting both. When you get a vector, you're getting its direction and you're actually getting its sort of foot-pound force. Does that make sense? So that's, it's weird. Like the answers to these questions are not numbers. They're vectors, which gives you the number n. So just to kind of draw a picture of this then, if I don't know if I can, but let's try. So if I said that's positive x, that's positive y, and this is positive z. So from here, what's the vector around which that's rotating? Well, I got to go positive in this positive 7 in the x direction. I'll say that's 7. And then 5 negatively in the y direction. Notice I went less. If this is 7, then maybe that would be 5. And then I got to go 12. What direction? Down. So that'd be quite a ways down. Maybe about there. And so would you agree that's vector m right there? Now, because of how I got there, can you picture the way that's pointing? You might be able to kind of picture it, but again, it'd be kind of cool to be able to draw it in 3D and spin it around. It's actually pointing kind of down. Well, whatever it is you're spinning, it's actually spinning around that axis. Does that make sense? So in 3D, it's not enough just to come up with a number. You got to say, oh, it's spinning around that axis. And there's something called the right-hand rule, which is this. If you aim your thumb along that axis, you see our fingers want to curl around your thumb. Your thumb is the axis and your fingers are positive. So if it was spinning positively, we'd say the thing is spinning like this. And if it was spinning backwards, then you could go, oh, it's actually backwards. So it's following, you put your thumb in the direction of the actual vector version of the moment, and then your fingers tell you it's positive. But it's kind of your right hand. It's called the right hand rule. Now you can picture it's like, don't you find your head just exploding, like trying to like, oh, you can see why this, if you will, needed to be automated. So, and notice in a sense, the 7, 5, and 12, like I actually did use those as distances, didn't I? Like I counted them as though they were distances, but they're not really distances, they're foot-pounds. So, but in order to get a sense of the direction for this, I was able to treat those like they were distances. As long as I kind of stay proportionate, that basically works. And if I take the square root, as I said, of 7 squared plus -5 squared plus -12 squared, somebody punch that in your calculator really quick, just so we have it down.
14.76.
Thank you. If your goal was just to sort of figure out, is something going to break? If I torque this up here so hard, some point snaps. If I want to know the number, there's the number, 14.76. But again, just to reiterate, can you see how if I just report the answer is 14.76, you've lost what direction that's being rotated in? So I could break this coding by doing this. Can I also break it by pushing down on this, and you can see it's working, right? So that's two different directions. And so the cool thing about the vector version of this is it's like it's got everything built into it. Isn't that kind of cool? But you got to be able to speak the language because it's pretty painful. So looking at your note sheet, that's exactly why this matrix kind of always has IJK up there, because you do have to keep straight when you break that force into 3 components, which is which. And as I demonstrated floundering around at the start of class, notice it is important that distance is here and force is there. Like you can't just put that in there randomly. Lastly, on the note sheet, so notice here I said the moment around O, because remember the rotation can happen around any point you want. Can you picture that? Can I get this podium to rotate around this point right here in the corner? Yep. Rotate, so there's moving, right? So what point are you rotating around? So we rotated around O, right? Because I said around point O. So this is the moment around O. And notice I said, oh, by the way, your answer to that's going to be a vector. Like you need to know that. You're not getting a number for this. And so it's R cross F. So the R is first and the F is second. R is the distance, F is the force. So that's what a cross product is. And so the problem is, what is a cross product? It tells you the moment of something. And so unless you're taking engineering, you're not going to understand what it is. In a regular math class, they're just going to say, this is how to take the cross product. And then all the smart students like, what is a cross product? And then it's usually like, I don't know, it's like how you multiply two vectors. But like here, we're actually doing something with it. So all of a sudden it's like, hey, that's pretty cool. Now, you may have noticed that process was pretty complicated. Can you see here that I actually kind of wrote out for you what you're actually doing? In other words, if you sort of get lost with that little process I just went through, like watch, do you see how it's written out right here? In other words, to get the I term, what do? You take Rx times Fy. What am I doing? Why am I lost? Oh, I'm in the wrong world. I was looking at this red going, what's going on? Remember we had to cross these out, right? So it's Ry times Fz, isn't that what's sitting right there? And then it's always minus Rz times Fy. And so that's always minus. So is that what we just did? So you can either kind of get the little trick down and not need to look at that, but if you want to just have that, there it is. And so notice this was a plus, that always is a minus. And then this is minus every single time. So there it is, kind of written out what you're doing. But can you see why somebody decided, hey, if we organize it this way, then you could actually memorize the process and not have to write out all of this nonsense. So you can kind of see the idea here. That's kind of cool. Okay. Go ahead.
Isn't there also a determinant of matrix?
Yes, it is. That is also a determinant. You're exactly correct. So now I want to just take 1 second here and actually kind of show you how this works. So we agreed a minute ago with the bike problem that we ended up taking the force of y times the distance in x, right? So let's see if we can figure this out in 3D. Now, first of all, you got to stare at this a minute and have me help you make sense of what we're seeing here. So notice positive z, positive x, positive y. And so this is the O around which we're rotating here. And so that's the point we're looking at. And so we're basically saying, okay, there's some point out there in space around which we're going to rotate. Let's rotate around that point right there. Now, in order to get this thing to rotate around this, does it make sense I got to apply some force somewhere? So if I put the force right on that point, does it make sense it's not going to rotate? I have to put it somewhere else. So let's put it right here. Put here. Now I could push down there, I could pull up, I could even pull in some totally weird direction. So the key is, where is the point around which we want this to rotate? And then where is this force somewhere else that's pulling or pushing? And notice it's like totally in some weird direction. It's not like it's automatically just nice and horizontal. If it was horizontal, it would cause this thing to spin around nice and flat, and it would just stay in a plane. But if I push way up in this direction, then this thing is going to like lift up in the air. I mean, it's kind of hard to picture what it's going to do, isn't it? So that's what you see here. So let's stare at this for a second. So do you see how they called this R? So here's the actual force. Here's the force that they're putting at some weird distance away from point O. And then R is that distance it is away. So it's like, here's how far it is away. And then that force is going off at some weird direction. Does that make sense? Now, as we saw with the bicycle, what do you got to do to force F? You've got to break it into its Y component. Notice that's parallel to Y. Its X component right there, which is, notice, parallel to X. and its Z component. Notice that's parallel to Z. So we're going to sort of not look at F, we're going to look at each of its individual components, right? And then the other problem is the distance. Like we can't use distance R, kind of that hypotenuse distance. We've got to break R into its components, R of X. Let's see, where is R of X? Notice this box actually helps us. Do you see what the box is doing? It's like, how long is distance X? It actually goes to right there. Why is that? Well, can you see where this point is? Like to get from O to here, you go over X this far, and then see what RY is? It's right there. You go over Y to there, so that's RY. And then you actually go up R of Z, which is the same distance as that R of Z over there. So you go X, Y, Z, and aren't you now at the base of that force? That's where it is. So again, all I want to do is just give you at least some conceptual, like, oh, I see where the quadratic product is coming from. So let's figure out how badly. Let's just do one of these. I'm afraid we're going to run out of time. I don't know, around the y-axis. No, let's do around the x-axis. Around the x-axis. See, the problem is we can't, what we don't want to do is try to figure out how it's rotating around some weird axis. We just want to do each axis one at a time. And so how badly does this thing want to rotate just around the x-axis thanks to those forces? Well, so notice it's very important. You're kind of staring at the x-axis. So we're basically saying how much does it want to rotate just around x? Well, notice that the force of x right here isn't going to cause any rotation around x because it's parallel to x. Do you see that? It's pushing in the same direction. So the force of x isn't going to do anything to get it to spin around x. We're talking about something spinning around x. And by the way, right-hand rule, force of x, if we're rotating around x, then that's positive. You see that? So I'm actually going to draw that in there. So if I went around that way, that would be positive around x. So can you see up here that force X is, because it's parallel to that, isn't causing anything to rotate around it? But let's look at force Y. Is force Y causing us to move around it? Well, remember you can move this. Maybe it's a little easier to see it if I move it to here. Isn't that force Y? How far is that from the x-axis? Isn't it force times distance? How far is that from the x-axis? It's that far. How far is that? Isn't it RZ right there? You see how this length is the same as that length? So it's actually force Y times, sorry, I wrote Y there, but it's Z, right? It's RZ. It's force Y times distance Z. Now again, that's not that weird because isn't that what we saw a while ago? It was like force X times distance Y. Now, is that causing positive or negative rotation based on what I drew down here? Notice it's causing the rotation because the arrow up here is pointing to the right. It's actually causing rotation in the other direction. So that's actually negative. You see what I'm saying? So if I'm doing this using the scalar approach, like I'm trying to picture all of this, which is what we're trying to do here for a second, I have to be smart enough to look at that picture and go, okay, that's this distance away. This is rotating. It's going that direction. Oh, we said this was positive because of the right. Oh, so that's actually negative. Say again?
I don't understand how that's negative, the rotation.
Is that spinning the x-axis in the negative rotation, the y component, the z distance?
Yeah. Well, because it goes that way.
Yeah.
Oh, yeah, that's one. Yeah, it's rotated. The y is the force of Y is rotating negatively on the RX.
On the
Right?
Yeah.
Yeah,
You seen it?
yeah, I was doing the right hand rule on the Y axis.
Yeah.
Yeah, so because the axis around which we're rotating is X, your thumb has got to point toward positive X. So this is positive X, that's my thumb, therefore that's positive. Hey, ours is going the other way, so it'd be negative. So, okay, cool. So force Y is actually trying to get it to rotate. Is force Z trying to get it to rotate? Let's see, where's force Z? So here's, let's switch colors. Here's force Z. So relative to the x-axis, I'm kind of confused. Okay, let's move it. Here's where it is. It's like right there, right? How far is that away from the x-axis? It's ry. So it's force Z times ry, right? Times distance y. Now, is that causing positive or negative rotation? So this is actually, see, if you're doing this with the scalar technique, you got to realize, whoa, one of those is positive, one's negative. Therefore, they're fighting each other. Very important to know that, because if they're working together, you're going to get a ton of rotation. If they're fighting each other, then it might not rotate at all. So the point is, one's got to be positive, one's got to be negative. So man, this is brutal. How am I going to automate this? Well, let's just stare at what just happened. Notice no X's showed up to the party. Like there's no X distances and there's no X forces. They caused no desire to rotate because the force was going parallel to it. And so how could we keep this straight? Well, if I think of this as the forces and this as the radiuses, then I could write radius y, radius z here, since alphabetically y comes before z, and I could write force y and force z. But how would I have to multiply those to get that to come out? Wouldn't I have to go ry times force z, which is this one, and then rz times force y, which is that one, but oh, this is supposed to be negative. How do I get it to be negative? We'll just put a negative in there every time. That's what you do when you do this. That's why there's a negative there, because these forces are always fighting each other. So I'll stop there, but if do you see why? I mean, this is pretty brilliant, right? Remember, I'm just showing you what somebody else figured out. Like, I'm not smart enough to invent this, but it took me a long time to actually see that and understand it. And that's so that the cross product on your note sheet is a really cool mnemonic device to automate this process. So I don't have to keep track of the signs. I don't have to keep track of which one's positive, which one's negative. I don't have to try to picture that thing in 3D. And you can appreciate that if I wasn't able to erase what I just did, if I did what I just did 2 more times with different colors, like that's going to be nonsensical. It's already nonsensical, and I have only done 1/3 of it. But that's kind of cool to at least get your hands on it, right? You can kind of see it a little bit. Okay, let's do a problem. So what do we got? I want you to stare at that just for a second. I remember my office is right next door. I forgot to grab them. So see if you can write out the matrix that we need to take the cross product of here. You have a copy of this on your pen.
Yeah. I love seeing the arbitrary like negatives get thrown in because I always imagine myself like you are like the guy who's like coming up with all the smart stuff. I'm like, right, okay, just throw the negative in there. It's supposed to be negative, just put it. Yeah, exactly. That's just how I operate. Like, it's supposed to be negative. Why is it not? She's like, dude, fuck it, just put a negative sign.
No one's gonna notice.
Yeah. You're like, wow, it's working every time. You're like, yeah, I fucking know. Like, we did it. Yeah, you're like, I just wanted to make it make sense. Like,
No,
no.
life doesn't make
Yeah,
sense,
don't do
bro. Yeah, quick way. Yeah, that's a skill on. It's like, just go with it.
That's kind of, you know, do you remember David Schmidt?
Sounds so.
Do you remember David Schmidt?
Oh,
He was super smart, bro. And so like that was something me and him were constantly studying together. And he was like, man, I don't understand how this works. And I'm like, who cares? I was like, we got the right answer. He's like, no, I'm gonna stay open more. He's like, I spent 3 hours, I figured it out.
Was he in our vector class?
Yeah.
Mary?
Yeah,
And yeah.
yeah, he was super smart. He would like say sometimes like, I think why? I'm like, bro, I just don't care.
I'm so excited to come to class. I could. So after class two, I've got this is straight out of your book, this figure we just messed with, but if you want to like write on this yourself and like try to make one of the other ones, actually do that. Okay, so what I have to figure out then to make sense of this is I got to figure out what point are we rotating around? Point A, okay. So that's right there. Now notice this is a little weird because it's a pipe. Don't you find yourself thinking it's not going to rotate around A, it's going to rotate around axis AB. Like it's going to, the question is like, is this going to unthread or tighten that pipe? And that's the second question. In other words, what's the torque around AB? In other words, how much is that going to, what's that going to do? Is it going to unloosen the pipe, so to speak? That's the second question. That's the second part of your note sheet. So this is kind of weird because it's saying around point A. What are all the pipes doing between it? It's just showing a connection so that it would actually rotate it. If I said, how's this force going to rotate that desk right there? You think, well, it's not touching it. It's got to be connected to it somehow. So all that pipe connecting it, it's not important except for A is not going to rotate unless there's something there. So there's A, and here's my force. Now, what's the problem with the picture with that force right there? It's a two-dimensional picture. I can't tell where that's pointing. Is that down, up? Like you can't tell. Like that's not, you can only tell if you get practice. You can't tell. But they did something extremely nice for us up here. What did they do in this problem? It already broke into its X, Y, Z components, which saved us the trouble of having to do this for ourselves, which we'll have to do for ourselves in just a second. Nice job. And so notice it says 600, 800, negative 500. So 6, 8, negative 5. So let's see, 6 in the X. I already forgot. 8 in the Y. And negative 5 in the Z. Oh, okay, now I can kind of picture what it's doing. You see what I'm saying? You don't need to, but that's just kind of cool to do. Okay, so for my note sheet, here's all I have to do. To find R cross F, I just have to set up this matrix, I, J, K. And first I have to put the radiuses, which is the distance from A, and it says this on my sheet, but to any place along this force. Any place you know. Now, in our case, this is the only place we know where it is. So basically, how far is it from A to C if I get there by only following X's, Y's, and Z's? I don't just go straight there. I go X and then Y and then Z. Well, to get there, if I follow the pipes, don't I go 0.5 in the X direction? But that's positive X. True? And then in the Y direction, I go 0.4 to get to there, but then another 0.3 later for a total of 0.7, also positive because that's positive Y. And then lastly, I actually go down 3, down, opposite of positive Z. So down 0.3 meters. You agree that's the distance? That's how far it is from the point around which we're rotating to the force vector, not from the force vector to the point, but the reverse, from the point to the force. Then we need the X, Y, Z components of the force. Sweet, they gave it to us in that form. Notice they didn't leave off the N at the end, which is newtons. These are newtons. So 600 newtons, 800 newtons, negative 500 newtons. Awesome. Now I just need to do the cross product. I'm done. Notice they said determine the moment of this force about the point. So again, that's a little nebulous. What are they asking for? Well, they weren't really specific, so I'm just going to leave it as a vector because then it can be done sooner. If they said, what's the magnitude of the force, then I would have to do the Pythagorean theorem on my answer. So I'm going to write the whole thing out. So to get I need to go this times this. So 0.7, let's see, I think I'm going to multiply it out instead of write down the, no, I'll write down the pieces, that's fine. No, I won't, I don't want to do that. 0.7 times 500 is 350, but it's negative, so that's negative 350. And then it's always minus, so I'm putting the minus now, and then it's 0.3 times 800, which is 240, except for it's the negative times a positive, so that's actually minus 240, isn't it? And that's kind of my x component. So I'm doing this because I don't have to look at a note sheet. That's kind of neat. So now let's keep going, switch colors. So if I get to J, then aren't I going 0.5 times 500, which is 250. Well, that's a negative 250. And then it's always minus. And then it's 0.3 times 600, which is 180, well, negative 180. And that's my J component. What am I missing? Yeah, this one always, the sign gets changed. So the first one is always positive, the second one is always negative, this next one is positive. And so last, to get K, I'm going 0.5 times 800, which is 400, always minus, and then 0.7 times 600, which is 420. And that's kind of my Z or my K component. So all I have to do is do that math and I'm done. I got it. My moment around, and notice the way I'm writing this, what point was it around? Point A. So I said moment around A, and I'm even telling you, hey, this is a vector answer I'm giving you here. It's not a number. Negative 350 plus 240 is actually negative 110, I think. Negative 250 plus 180 is negative 70, but then this negative changes it to a positive. And then 400 minus 420 is 20. So there we go. There's the answer. I'm done. If I didn't make any dumb mistakes. Am I wrong anywhere?
Yeah.
What's wrong with K?
400 minus 420 is negative
Negative 20. Thank you. Thank you.
You'd have found it eventually.
Now, just to kind of visualize this a little bit, again, this is like a force pulling off in some totally weird direction. So let's just try to make sense of what does this tell us again? So if I go from A, and now I'm going to measure negative 110 and then positive 70 and then negative 20, I'm going to go to that point. Now remember, those are, well, what's the unit of this? This is a moment. What have we been doing? These were meters and these were newtons, and we multiplied 0.3 meters times 600 newtons. These are Newton meters. That makes sense? That should be there. Like I shouldn't leave that off. So from here, although that unit is Newton meters, I'm thinking of this as 11, 7, and 2, just so I can get this proportionally right. So, okay, this isn't good. I'm afraid I'm going to go off the page. Well, let's try it over here in this picture. So I need to go backwards in X11. Notice I'm staying parallel to that. So there, so I'm calling that 11. Everybody happy with that? And then where do I go in Y? Positive 7. And so I'm trying to stay parallel to this Y-axis over here, positive 7, which is about that far. And then Z, negative 2. And so, Huh? Can you picture it's like, oh yeah, that totally makes sense. What does that represent again? That represents the axis around which this thing is gonna rotate. If you rotate A, it's gonna wanna rotate, notice my thumb, it's gonna wanna rotate around that axis. That's not the direction it's rotating, it's this, it's rotating around that axis. And can you see that that kind of looks perpendicular to this? It's kind of hard to visualize.
So my question, it seems like RMA is not the F down there, right? I guess that F is like, would be our magnitude.
Yeah, so if I took 600, 800, and 500 and did the Pythagorean theorem, that would actually be the force on F. So I actually don't know what force F was because they gave it to me as a vector.
But that force F is causing our moment.
That's exactly right.
So,
The force side, what they give us was just the direction of it.
right. So is that force F pulling down and towards our A point?
No, away, down and away.
Yeah, we said it was going 600 this way, and then 800 this way, and then down 500.
So you would kind of, it would snap, but
Oh, and so,
if you were able to move the whole thing, it would rotate on where the moment is at. It's just basically creating a new axis in which it's going to be rotating. That's just the magnitude of it. That's how much force you're applying. Or how much force is being applied on that.
So notice you can figure out that there's 132 Newton meters of force trying to get it to rotate that way if you want to. That's cool to know. So in the end, it's kind of cool that you can actually get this right and sort of not be able to even visualize it, right? It's really hard to visualize. Let's do another one where we aren't quite so lucky. I like this one a little bit more because it's kind of like a trap door or something like that. But notice the force here is 80 pounds, like we actually know it this time. But that's not so good because remember, we got to have it in vector form. So now we got to put it in vector form ourselves, which sucks. We've done this a little bit, but we certainly need practice. Notice it's hard to tell where that force is going, but thanks to this little kind of dot, 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 this chain, do you see how it shows it's actually connected there to the ground? So that for that reason, we can see where it's pointing. We can see where that force is pointing. Now, again, would you agree if you pulled on that, does it make sense that's going to want to open the door, so to speak? But isn't that a weird direction to pull on the door to open it? It's like pulling totally sideways. Can you picture that one hinge is going to have to work harder than the other one? Like if you pulled too hard, probably that B hinge would be the one that tore off. And so does it make sense? The real rotation here is kind of around axis AB. Like that's the, but notice this question is actually asking the same thing it asked before, which is determine the moment of the force around just A, like just around that hinge alone. Which again, it's kind of a weird question. We're actually going to reconsider this in a second. We're going to reconsider this around AB, the entire two hinges combined. So this is the same problem we just did. You agree with that? Except for they weren't so nice with the force. And this is also going to take some calculation. I'm going to go kind of fast here, so interrupt me. But let's figure out the force as a vector. Well, where is this thing pointing? It starts here and points there. So we got to travel from C to D. Does that make sense? How far do we travel to get from C to D? Well, let's see. How am I going to get there? Let's see. I think I'll go this way first. So that's negative Z, right? Is that dimension given? Is there some way I can see what that dimension is? So I'm going to do that first, and then I'm going to go along this line. Notice I'm staying parallel to the axis. I have to go. That's the only way I can get there. So I'm going to do that second, and then this third. You agree with that? Now that's not X, Y, Z. That's not an order. It's just those are lines on the paper that I can kind of see where I'm going. And so notice I know this one, it's 5. So what is that? 5 what? Say again? No, it's a little worse than that. Is that X, Y, or Z? It's X. And is it positive or negative? So that's actually -5 for X. You agree with that?
Are you using the origin as from C or?
Yeah, no, see, yeah, we're going from C. Like the origin is not the origin. We're going from where the vector starts to where it goes. We're inventing our own origin. It's how far do I have to go to get there? So my distance wise, I have -5 for X. Do I know Y? Do I know X?
Do some trig for water.
3 plus the.
Yeah. Notice it's like I know this part is 3, but then there's this length. And so why did they tell us 45 there? Because they actually told us the door was 4 feet long. So yeah, I got to or get to do some trig here. So that wasn't very nice. So if that's 4 and this angle's 45, yeah, and then this angle right down here is 90. So thankfully it's at least a regular trig and not law of sines and law of cosines. So I won't belabor the point with this, but if you did sine and cosine of that 45, both of these are 2.83 approximately. So that means my Z straight is what? It's not 2.83.
Oh, from D to C, negative.
It's down, right? Didn't I start here and go down? So it is 2.83. It's just it's negative, and we can't get that wrong because I went down. And then in Y, am I going positively or negatively?
Positive.
Positively, because we're going toward Y. Z was negative because we went down. So that'd be 3 and 2.83. So that'd be positive 5.83. So remember, there's a connection between the actual forces in XYZ and the distances in XYZ. We were able to ascertain through some pain what the distances were in XYZ. And so would you agree that 80 is actually the hypotenuse of our gigantic system of right triangles? Well, for that reason, we need the hypotenuse of this as well. In other words, we literally need distance CD. We need to know how far that is. We know how far it was to get there by going X, Y, and Z. But if we do the Pythagorean theorem on all of those, and I'm just typing this in my calculator. Again, interrupt me if there's something bugging you. 5 squared plus 5.83 squared plus 2.83 squared. And I know I've rounded those off, so this is going to be off a hair. That's the kind of problem that I might look in the back and I'm off a little bit because I'm rounding. I got about 8.19. So now we actually know what proportion is X, Y, and Z. So if we take our 80 pounds and we multiply by -5 over 8.19, that's the proportion that will be X. Do you see that the X distance is -5, but the hypotenuse is 8.19. So just like these distances are proportionate, then if I multiply by 80, then I'll have the proportion of the 80 that's in the X direction. Isn't that cool? Should hurt your brain a little bit. And then isn't, for the same reason, my Y equal to the same setup and my Z equal to the same setup?
Next page is 4 stuff.
And so that's exactly right. That creates my force as a vector. I had my force as a scalar, 80 pounds, but that doesn't do me any good, just like the bike problem. We knew how much force was going, but unless we break it into X, Y, Z, this is totally confusing because we can't get distances. So if I take 80 times -5 divided by 8.19, I get about 48.8. And it comes out negative. Again, I'm rounding the way I want to. I don't know if this is right, probably rounding too much, who cares? And if I take 80 times 5.83, I get 56.9 positive. And if I multiply that by 2.83, then I get 27.6, except for it'd be negative because I'm multiplying 80 times -2. Now remember in the last problem, they just gave us that. That's where we started. This problem, we had to suffer to get that. We have to know the force broken into its X, Y, Z components. Last time we were given it, this time we had to suffer and get it for ourselves. How do I check and make sure I didn't blow that? Ton of things I could screw up here, right?
Take a magnitude.
Find the magnitude, do the Pythagorean theorem on that X, Y, Z, and it should come out 80, right? Now, will it? No, because I rounded it off, but it's going to come out darn close to 80, and then I'll know, okay, good, I didn't screw that up. And maybe one of you punches that in and make sure we didn't screw that up. And so, pretty close. Okay, good. So that means we didn't blow it. Okay, so now I think we're ready to do what we did before, which is to find R cross F. Remember, because this is the moment around A. So maybe I'll even write that in here. The moment around A as a vector would be equal to this cross product. What is that cross product? We always write I, then J, then K. Then we list all of our forces, but the forces had to go down here. Being careful not to lose the signs because this awesome mnemonic device won't work if we get our signs wrong, and there's signs everywhere, as you've noticed. Now I need the distances. Now again, to remind yourself, looking at the note sheet, what is this R thing again? It's the distance from O, the point of rotation, to the force. So how far is it from O? And notice right here, I said this out loud before, but what? Any point? You can go to any point on that force vector. That's crazy. Is that true? That's almost hard to believe. In this particular problem, you actually have an option. We know where both the tail of this vector is, it's right there, and we know where the head is. So we need to go from A to either C or to D, and either one will be the same answer. It's not hard to believe. And doesn't A to D look easier? So let's see, from A to D. Remember, we got to list X, Y, Z. How do we get there? We got to stick with X, Y, Z to get this to work. So from A, let's see, I go that way 1.5. So isn't that positive 1.5 because I'm going toward positive X? And then I go, once I get there, then I go this far to get to D. How far is that? Isn't that 3 right there? And how far do I go in Z? Both A and D are on the ground, aren't they? So I go nothing in Z. So there's my distance from the point around which we're rotating to some place on that vector. And so that's going to be the easiest. But before we go on, let's find the distance from A to C. Yeah, good. Why does it work though? That's a great question. Why would that work on any point? thought I knew this. I thought I figured this out once, but I'm staring at it now thinking, I mean, I think the simple answer is if I said, hey, here's some wind, like blowing along that line, does it make sense that can move? Now, it can't move like this because now it's blowing a different direction, but it can move parallel. Does that make sense? So that vector can kind of be anywhere.
Is it because
In a
there's
sense.
a side for that whole line?
So yeah, I mean, in a sense, that arrow, this arrowhead right here stops, but it's not stopping anywhere in particular. Does that make sense? It's just saying, hey, it's going that way. And the 80 is actually its length, if you will. But I think it's because that vector can kind of be any place along that line. I think that's the simple answer. But I will say I don't really feel that good about that. At least I did one time, and now all of a sudden it's like I don't have in my brain what. So
C, the point C is the one being out of it. But then D goes.
yeah, and I think it also has something to do with like if I come over to this desk and I say, hey, let's push on it right there. Does it make sense? That'd be the same thing as if I came over here and pulled on it right there. It has something to do with that. I do offer random extra credits in this class, and this will be one of them right here. So let's do A to C really quick. So let's see, how do I get from A to C? Wouldn't I go, let's see, I'll cruise along this line. How far is that? It's 5 and 1.5. What direction is that? Is that X, Y, Z, positive? It's positive X. And so I got lucky, X came first. And so X is 6.5. And let's see, I need to get there. So let's keep going. Let's go this way. Well, isn't that 2.83? Is that X or Y? It's Y, but it's backwards, right? So it's negative Y. So that's negative 2.83. And then I'm going to go this direction, and I made it to C. But wouldn't that be positive Z? So that's actually 2.83. So we're basically saying you could have used either one of these vectors. I could have put this in here. So for extra credit, at least convince yourself that this is true. Like go do it again with that one in there, and then whoa, we get the same exact answer. This one was easier to find, and it also has a 0 in it, which is going to make my work a little bit less, which is kind of interesting. But now we're ready to roll. So, and I'll write this a little different. Last time I put I at the end, remember I doesn't really do anything other than just keep a place value. So this time I'm going to write I first, and then I go 3 times 27.6, 3 times 27.6, that's a negative number, is negative 82.8, always minus, and then 0, oh sweet, 0, so I don't have to do anything with that one. And then J was always negative, so I put the negative in there right now. And then J would be 1.5. Let's go pink. Pink never gets any play. 1.5 times 27.6, but that's negative. So I got negative 41.4. And then, oh, again, 0. So always minus, but 0. And then this next one's always plus, but now we're switching to K, Z. And so K would be 1.5 times 56.9, which is, and that's positive times a positive. So that's 85.35. And then 3 times negative 48. So it's always minus, but then 3 times negative 48.8. So that's a negative number. So that's negative 146.4. So that gives me negative 82.8 for my I, minus a minus. I ended up with a positive 41.4 for J, and then 85.35 minus a minus is actually plus 146.4. I got 231 for that, plus 231.75. Okay, so there's my moment around A as a vector. And I just kind of think, huh, cool. I mean, I didn't think about it. I'm checking to see if I got the same answer last time I did this. Yeah, I did. What's the unit for that I was lazy to leave off in this case? What were our distances? What were our foot pounds this time? Now notice we got lucky. What if those distances had been in inches? Well, that's okay, inch pounds. But that's not something that you should leave off. A foot pound is not the same as a Newton meter. Thank you.
So we should get the same answer if we put in the distance for AC, right?
Yep, if you put the distance for AC in, every number will look different, but when you get down to the final answer, oh my God, it's exactly the same.
When you say every number will look different, it will look different.
Yeah, it
It's
won't.
like I
Yeah, it won't look different here, but these numbers, like this won't be 82.8 minus 0, it'll be 75 minus negative 13 or some weird number, but then it'll end up 82. So again, we're getting the vector around which this rotates. I won't take the time to make sense of that, but let's take a quick look now, because we're, as always, out of time. What's the difference between, notice I bolded this, around a point? That's what we've been doing, but what if it's around an axis? What if you don't want to know that around an axis? What if that's what you're doing?
don't get to it.
No, I refuse. Look how ugly that is. You're stupid. I'm out of here. What's the same? What's different? Check, check. Yeah. What do we have? We don't have IJK anymore. We have U of AX, U of AY, U of AZ. What the heck? Well, notice axis A. So that's the unit length of axis A. Well, the X component of that unit length.
You have like a picture or something that relates to that?
Yeah. So we need to do.
An example?
Well, if we did the example we just did, would U AY just be 5 feet because the distance between those two things? That's why.
But if you necessarily revolving around a point.
So what if we redid the problem we just did? Except for we asked a different question. Dun, 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 dun. So notice I kind of wrote my own question for that. I used the same picture, but I just made up my own kind of problem for it. And I think this will allow us to go kind of quickly. Let me you stare at your note sheet. Just give me a minute. I don't have this one on my iPad. Let me see if I can get it on there really quick. Oh man, this sucks. I wasn't sharing my screen the entire time we recorded this, so there's actually nothing to look at. That's not true. I was. Forget it. Never mind. We're good.
You forgot to buy your coffee today. Huh?
Now I bought two.
You're all over the place. Looking fly as heck though with those Converse.
Oh man, I'm not acting my age today, am I? Google Drive. That's
So
it.
man, I told my wife, I was like, I'll always wear Converse. No matter how old I am.
So the difference with me is 9th grade basketball. This was like our basketball shoes. Like that's what basketball shoes were.
Yeah. I played.
Now they're back like as a fashion symbol. That's so funny.
Oh, they have left the Sandlot.
those were next, right after Converse, bam, Nike high tops. I'm so far behind the times, I'm ahead.
What would be our R vector?
I think I can make this work. I'm almost ready. Bam. Okay, here we go. So not determine the moment of the force at A, but around, isn't this what I said on yours? Around axis AB. So that axis right there. Notice AB, like sort of, it's a direction. Does that make sense? Like it doesn't matter how long AB is. It's like 50 feet long. We're just talking about an axis around which it rotates. And it could be that long, it could be like the end of my finger. As long as you have a straight line, then we've got an axis, right? So that unit in the formula sheet is basically saying we need a direction, but remember we're doing a lot of multiplying by stuff. And a second ago, we multiplied 80, was that the force a second ago? Oh, it's on here, 80. We took 80, what we multiplied it by, well, what your book calls a unit length. We multiplied it by a unit length. Let's look back at that really quick. If y'all want to, if you took this right here and did the Pythagorean theorem on it, what do you think is going to happen? In other words, not the 5, 5.83, and negative 2.83, but them being divided by the hypotenuse. You actually get 1. That's we took 80 and we multiplied by something, but see, we don't want 80 to get bigger or smaller. It's still 80. So we multiplied by a unit vector. We multiplied by a unit length, but it's proportionally set up in such a way that it divvied up 80 correctly into each condition. And so that had length 1. I would encourage you to type that mess squared into your, and you're going to get about 1. You won't get 1 because we rounded off 2.83, but you'll get about 1. And so that's kind of what we got to do here. That's what this note sheet is saying, is we got to stick with, that's the only thing difference. UA, X, UA, Y, Z, they're the Cartesian unit vector lengths of axis A. So we got to make the hypotenuse of it be 1. In other words, it's got to be, the length of that vector has to be 1. And that's because we're multiplying it by stuff, right? So if we're multiplying it by stuff, we don't want it to change just because of the axis, because the axis just tells us what we're rotating around. That's the logic of this. Now, fortunately for us, this is really easy in this particular problem, because do you agree axis AB is actually parallel to what axis? Which direction is that going? It's just going in X. It's not going in Y at all. So my pen in the room right here, I'm in the corner of the room. That's X, that's Y. We'll call that Z. And my pen is pointing off in some weird direction. Does it make sense? I got to establish a little tiny X and a little tiny Y and a little tiny Z. But what if it was just going this way? Hey, it's just going Y. It's not going X at all. It's not going Z at all. Well, then I could just think of this as length 1. Like that's the only length I have to concern myself with. I don't have to make up that weird Pythagorean number. I just have to say, hey, that thing is 1 in the X direction. That's it. So, that's good and bad. That'll make our problem a little easier, but this probably isn't the best. The problem is there's not actually any good problems in the book. What you really need is a weird axis and a weird force, both, to get a good picture of how this really works. But we're out of time, so that's okay. So axis AB is, well, anything in the X you want. Like you could say, how far is it from A to B? Notice it's 1.5 and then 5 all the way to here and then back 1.5. So isn't it just 5? Isn't AB like AB, the length of AB is actually 5? Well, 5 in the X, 0 in the Y, and 0 in the Z. So see, what we would have to do is Pythagorean theorem, the X, Y, and the Z, and then we would have something like we just had a second ago. We'd have like 1/9 and 3/9 and 7/9. We'd have numbers for all of them. But in this case, that's how long each of them are. So if we take, so the hypotenuse is 5 and the length is 5. So the hypotenuse is actually 5. And so we're actually thinking of our axis then, our U, what did I call that in the note sheet? Our U of X. I'm sorry, U of A, I guess you would say. Our U of A is actually 1, 0, 0. So that describes which direction our axis is going. 1 in the X, nothing in the Y, nothing in the Z. Now again, it doesn't say where it is because it doesn't matter. It's just parallel to the X-axis somewhere. And so then I can steal everything else that I just had because the R's and the forces we calculated them a second ago. So the moment is this determinant then. What did we say a second ago? Quickly, come on, man. Wasting our time. Oh yeah. 1.530. This was negative 48.8. This is 56.9. This is negative 27.6. Now, thanks to those zeros on the top, that's going to be a really nice, that's going to be a really easy determinant to take because it's going to have a lot of zeros in it. The other thing that's interesting is this, because that top row is not letters this time, but numbers, we're actually going to get a single numerical answer to this. In other words, if you know the axis, then you know which axis it's rotating around. Therefore, I want a numerical answer to say this is how many foot-pounds of desire it has to open. Does that make sense?
We don't have to focus on the direction.
Yeah, the direction is given because we said axis AB. Like there's your direction. It's AB.
What if your axis is just out and over? Oh, it's actually never specified maybe.
Yeah. So if it was out in the middle of nowhere, it just wouldn't be 1, 0, 0. It'd be 0.7, 0.2, 0.3, or something like that. And so that would be describing, what direction that thing's actually going. And the Pythagorean theorem of those three numbers would be 1 because we're multiplying by a distance of 1. We don't want to screw up the number. So that's why this has to be a unit vector whose magnitude is 1. So does it make sense when I cross out this row right here? That's kind of like my I. And so I'd have 3 times negative 27.6 minus, well, 0 times 56.9. And then the other ones are going to be
Are we multiplying by the 1, 0, 0 top?
well, no, just this. Well, hey, wait, this isn't an I anymore. That's actually a 1, isn't it? That's not I, it's 1. But then the other ones are just going to be gone because they're going to have zeros in front of them, right? So this is the only one. So you should be thinking, well, wait a second, what's that saying? 3 times 27.6. So I actually end up with negative 82.8 foot-pounds. Huh? And that is not coincidentally the X component of the one we just did a second ago. But basically what this is telling us is how badly the door wants to open. Does that make sense? Like, is the door going to open? You can appreciate if that's a heavy door, the hinges are creaky, and you pull on it, it might not open, right? And so this is how badly that force is causing it to want to open, and maybe that won't be enough.
Out of curiosity, this is working perfectly because AB is going that way. I found the right hand rule matches up. But if we went BA, you're like, shit's noodles. It would be positive AC, wouldn't it? Because our right hand rule is wanting us to curl the opposite way.
Yeah, isn't it interesting? Because it's kind of like, we're getting a number here, but you know, which,
I just don't know how it would.
in order for that to be negative, so I'm pointing my thumb along AB right now, and it's actually going this way, right? Wouldn't that be positive? If this came out negative, so then it's kind of like, it's this way, right? Which kind of means so it's like, notice there's nothing there that's kind of telling us which direction it's actually going. And I think that has to do with, since this is positive X, then this way would be +1 for our distance, whereas going that way would be -1.
Right. So if we were going BA, we would just have that negative one.
Yeah, so it's interesting because like, this is sort of like from B to A. No, that's not true because it's from A to B. Yeah, so that makes sense because we called it this one, right? We said it's +1 and it's like, no, it's not opening that way, dude. It's going the other way, right? So the signs are working, like it's taking care of itself because we called that positive. That's why that happened.
On the AB, the 5 is just, you pick it. Point.
Well, I picked it because that was actually a distance. Usually you have to pay attention to those distances because the X and the Y won't be zeros. I'm sorry, the Z and the Y and the Z won't be zeros. So I'll just do this on the board really quick. But what if I went from here to here? Actually, I'll do this in a second. Let's say we went this way 2, and then we went this way 4, and then we went that way 7. And so this is A, and this is B, and so we're interested in axis AB. That's the axis around which this is going to rotate. Now, because this is +Z, this is +Y, and this is +X, then I guess the length version of that of AB as a vector, if I think of kind of AB as a vector, it'd be, let's see, that's +7 for X, right? +4 for Y and -2 for Z. You agree with that? And so if this was the axis and I had to stick it in there, what do I do?
Take the Pythagorean theorem of that.
Exactly. So the square root of 49, 16, and 4, which is square root of 69, which is about 8.3. So then our AB as a vector, well, as a unit vector, would be each one of those divided by, what did I say, 8.3? 8.3.
That's squared. Yeah, Pythagorean theorem, all that.
Yeah, now if you Pythagorean theorem this now, you're going to get 1. And so, and because we're multiplying these by things, what we don't want to do is change the size of them. That's why we don't multiply by 7 and 4 and 2, because then that's going to make the Newton meters like a huge answer. This is now a direction without a magnitude, a distanceless magnitude. So that will get it going the right direction without screwing up the size of it. Does that make sense? So that's why we're making a unit vector out of that thing. We just got almost, that example is almost worse because it's kind of like, wait, where'd the 1 come from? So it's like this distance was 7, so we had to call it 7, but later it got modified thanks to the hypotenuse. But in our case, I said, well, that's distance 5, but then the hypotenuse was 5, and so.
So what would we put in our IJK in terms of that?
This is your top row.
Yeah, the
So we would put 7 over 8.3.
This would be our top row. So instead of 1 here, I'd have 7 over 8.3, and then I'd have 4 over 8.3, and then I'd have 2 over 8.3. And this would have had a lot more components, but it still would have came out 1 number though. It still would have been a number, not an X, Y, Z separately. So you're actually getting a literal Newton meters or foot pounds of how badly that door kind of wants to open.
I would have, I'm glad you specified, I would have put 7, 4, -2, I wouldn't, what was it called again, making it a unit vector?
Yeah,
I wouldn't have like unitized it, or however you said that.
For the 1.5, we can also use the other one, correct, for 8 to C.
yep.
Could we have used also B to D or? They didn't specify to use, oh, yes, it did.
Yeah. The only thing we know about our force vector is C and D. That's the only two places we know that describe it.
Yeah, so for R. We use one for A to D. Let's use B to D. The other hand instead of the A hand. It doesn't tell us we're going to use the A hand.
You're saying if the problem we just did or the one prior to that?
No, the one we just did right now.
Yeah.
For the R vector,